It's my first time here in Prague, so yeah, thanks for having me. Yeah, like Vojta said, I'll be talking about kind of foundations of cooperative AI. The way I usually think about that is like the study of game theory, but specialized for AI agents. So for people who haven't heard this definition, game theory is usually just defined as the study of strategic interactions between rational agents. And the way I think of cooperative AI, which is somewhat more narrow than probably what Lewis was meaning, is that it's basically just game theory for AI agents. And then the cooperative part comes from focusing on achieving cooperation. So kind of the key questions are like, one, how are strategic interactions involving AI systems different from those involving humans or firms? And can we leverage these things to enable or sometimes prevent cooperation? And by cooperation, I will basically just mean Pareto improvements, which just means like making all parties better off by their own values. Okay, so why would we care about this? Lewis already talked quite a bit about this, so maybe I'll speed through this a bit. But like, one reason is that like in the future, if we kind of like succeed on alignment, like AI might just get like very powerful, and we'll have like these like AGI or even super intelligent AIs just like running basically like the world. And if there's multiple of them, and at least one of them is aligned, then we probably want them to be able to like cooperate together and not like one's running the US military, one's running the China military, and like they get us into a huge war with like future weapons or whatever. Also, like we might have AI run companies. There, like it's a bit less clear. Sometimes we want them to cooperate. Maybe, you know, human governments would be too slow to govern AI companies, and so we want some ability to avoid like race to the bottom or like avoid like all polluting because we're in some kind of prisoner's dilemma. But also like in some cases we don't want collusion. Okay. Another case is a kind of more intermediate case where we have AI agents, but they're acting on behalf of human supervisors. Here, like assuming the AIs are basically aligned to their supervisors, we just like straightforwardly want cooperation. And here, you know, we're thinking about how to leverage properties of the AIs to achieve cooperation between the humans when like maybe the humans themselves couldn't achieve that. So why is this so slow? Okay, and one more which Vojta will maybe talk about up there, maybe talk about later. Game theory is just potentially an important tool for thinking about evaluating AIs. So it's kind of like a game theoretic interaction between like AI supervisors and the AIs they're trying to evaluate or maybe trying to do AI control on. And so here we can kind of use game theory to formally model affordances that these researchers might have. They can simulate the AI, they can like change its context or memory, things like this. Yeah, and here, like probably we don't care as much about benefiting the AI. But yeah, Vojta might talk about this. There are some reasons why you still might. For instance, like the AI might be like more willing to help you with your scheme if it also helps the AI. Okay, so this is like, yeah, broadly my motivation. My motivation for the talk is to kind of just try to give all of you some sense of like what's going on in this field of foundations of cooperative AI, kind of trying to give intuitions that like you won't get just from reading papers, like why people care about things, why these results are the way that they are. Yeah, so in service of that, please stop me and ask questions if you have them. Yes.
Sorry. Just because I said it. The question is, how much do the motivations and the framework depend on control of the agents? So that they stay controllable, that they're incorrigible. Like in the beginning you mentioned AGI, ASI, where maybe control is not assumed anymore.
Yeah.
Or are we still assuming that to some extent we can still turn them off, we can still intervene, we can still retain control over what they do?
Yeah, good question. So yeah, on that first case, the AGI, ASI case, I'm not assuming that there's human oversight anymore. I later on mentioned AI control, and in that context, I was referring to the research area that like Redwood Research is pursuing of like, we have human-ish level AIs that are like potentially misaligned. Can we still get good work out of them without like risk of takeover? So there's, yeah, that setup's like, okay, we're gonna have this AI write code for us, and we're gonna have like another copy of the AI like evaluate whether that code seems risky. The overseer AI doesn't know that like whether like it's one of its friends trying to like write a backdoor to coup, or whether it's like a human-made input, and so there's some constraints there.
Okay.
So yeah, is that?
In the first case, if control is not the assumption and alignment is the assumption, that they won't go after humanity, that's the assumption?
Yeah, like I largely think about it as, if we do go that route of like powerful kind of autonomous AIs, alignment is like very helpful, obviously, for like good things happening, but it's not sufficient because if we have multiple AIs, we also need them to play well with each other. And so if we have at least one AI aligned, we probably like, then we would benefit from, we ourselves would benefit from those AIs cooperating. Any other questions? Okay. Okay, so first I will just give some very brief background on game theory. For the purposes of this talk, you can think of a game as a matrix, payoff matrix. So these are just static games represented in normal form. You have two players for this talk. You have a row player and a column player. In this case, it's a game where each player has two actions. So the row player chooses which row to play, swerve or dare, and the column player also chooses which column to play. In this case, they're also called swerve or dare. And then from their choice of actions, you get payoffs. So the first number in each cell in the matrix is the first player, the row player's payoff, and the second is the column player. So like if the first player plays swerve and the second player plays dare, we get 2, 6. That means the first player who swerved got 2 and the second player got 6. Okay, those numbers, those payoffs are called utilities. The words or actions called actions. We have pure strategy profiles, which are just single actions. I always take one action. We also have mixed strategy profiles, mixed strategies, where you have a probability distribution over actions. So like 1/3 swerve, 2/3 dare is a mixed strategy. I think we can skip that. So and then we say an action is a best response against a particular strategy of the other player if it maximizes that player's utility against that strategy. So for example, if the row player is playing swerve, then dare is a best response for the column player because they're basically choosing between 6 by playing dare or 4 by playing swerve, the left or right column. And actually, like this is also a Nash it's also a best response for the row player because if they're playing swerve and the other player is playing dare, they're choosing 2 over 0. If both players are best responding, we call that a Nash equilibrium. Okay, so this is also a Nash equilibrium. There are also mixed Nash equilibria where both players or some players play mixed strategies. In this case, if each player like mixes uniformly between their strategies, like they're exactly indifferent between the strategies, and so they're willing to play both with probability 1/2. So yeah, 50/50 on both is also a Nash equilibrium. Does it work? Oh, okay, thank you. Okay, there's also another solution concept we'll use. I'll try to finish this game theory quick, which is dominant strategy equilibrium. So a dominant strategy is stronger than just a best response. It's a best response to anything the other player could be doing. In this bottom game, it's prisoner's dilemma. Defect effect is a dominant strategy equilibrium because defect is a dominant strategy for both players. So yeah, I think people know that. Okay, so now I'd like to get into like a kind of very classical area of work in cooperative AI that I think illustrates a lot of what's going on in the field pretty well. So this is called open source game theory. And the idea is that instead of playing a game directly, we're going to have two players, and they play by submitting a program, like in Python or whatever, and then this program will play the game on their behalf. Okay, and then the key assumption is that, like, so far that does nothing, except we're going to assume that the programs can read each other's source code. And so now, as I said, in Prisoner's Dilemma, like defect effect is the only thing that can happen. Essentially, it's a dominant strategy equilibrium. Now, if we assume that we submit programs to play for us, we have other equilibria. For instance, if we both submit this program, which just says cooperate if the other program is identical to me, otherwise defect, that is a Nash equilibrium. And I probably want the payoffs, but maybe I didn't put them here. Okay, basically the idea is that like cooperate is better for both players than defect effect. And so if the other player is submitting this program, you can submit the same program and get cooperate, or you can do anything else. They will defect. You will either cooperate or defect. Both of those are worse for you than submitting this program. Any questions? Should I? Yeah.
Microphone? Yeah, so consider a future situation. What do you think is probability that agents in the future will know like base model of other agents with which they interact?
Yeah, base model meaning like they're LLM based or just know their source
For
code.
example, this is really the truth, and game theory changes, and you know how act other agent. Or for example, if you know that it's the same agent as you are. So the question is, in the future, it may be a situation then one or two agents based on the same LLM model, so they behave the same, and if they know each other, then it's change the situation.
Yeah, yeah, great question, great point. I think I will talk about this later. Yeah, maybe proximally, I don't think that this program equilibrium model is necessarily like super realistic, but it illustrates like that things are different and the results are very similar to results in lots of more realistic cases, which is why I'm starting with it.
I mean, I just think that it will be an open situation compared to human situation, because we're all different, but models often the same.
Yeah, I agree. That is another important thing. So, yeah, we might have. Yeah, I think we don't know exactly what worlds with lots of AI agents will look like. Will they look like lots of very different AI agents in the way that different humans are different, or will they look like a few or like lots of copies of like two different models? Which I think is important. Yeah, I think I will talk about that later. Okay, I want to. Can people put thumbs up if they want me to go faster, thumbs down if they want me to go slower, sideways if it's the same? Okay, somewhat faster, but maybe I'm doing okay. What the heck? Okay, okay, so does this like program equilibrium model solve everything? No, for lots of reasons, but one reason is that this is super brittle. And it requires a lot of coordination, right? So if like we both try to submit the exact same we both try to submit a program with this idea, but we use slightly different syntax, we're gonna both defect on each other, and that's bad for us. One paper that kind of takes a different approach to get around this, still in the program equilibrium model, is to look at programs that try to prove things about the other player's behavior. So we're gonna look at programs that are like, I will cooperate unless I can prove the other player defects on me. And by prove, like proving things in general is like a, like undecidable problem. So we're going to assume that like we only look at proofs of length at most k for some like large k. Okay, so we have programs like this, right? Like defect unless I can prove they cooperate with me, or cooperate unless I can cooperate if I can prove that they cooperate with me if I do cooperate. So my cooperation like causes them to cooperate. Those are some like ideas for programs you might submit here. And the paper basically looks at like what happens when these programs play each other. I want people to guess the results. So if we both submit a program that says defect unless I can prove that you cooperate with me, what do people think will happen? I guess thumbs up, cooperate, thumbs down, defect, thumbs sideways, something else. I'll give it, yeah, maybe some time to think. Mostly defect, I think. So, which I think is the intuition a lot of people have. Like we have two programs, like they both are kind of waiting for the other to cooperate. No one's gonna make the first leap and cooperate, so like they'll like just run out and both defect, time out and both defect. Anyone want to guess on this other one? Cooperate unless I can prove that they defect. What happens? Both cooperate, both defect, something else.
One cooperate, one defect.
Okay. Okay, some people saying both cooperate. Turns out very counterintuitively to me, and I think most people, the defect unless I can prove you cooperate, cooperates with itself, and the cooperate unless I can prove you defect, defects on itself. Yeah, I think it's like some weird Loeb's theorem stuff. I don't understand it, but it's cool. If you like this kind of stuff, you should go look at this paper. Another approach to this like fragility with program equilibria is robust program equilibria. And the idea here is basically, okay, well, if we were playing repeatedly, a good strategy that empirically does well is tit for tat. So I just do whatever you did last round. And if you know that, you want to cooperate with me now so that I cooperate with you next round. Yeah, this cooperates with itself. If you start by cooperating, it also can't really be exploited because if it's cooperating, that means the other player is cooperating. And so the idea is to try to make a program equilibrium bot that does this. The most obvious approach is just simulate my opponent and do whatever they do against me. But this, like, if you play it with itself, it will never halt. So we have this thing called epsilon grounded fair bot, which is going to do that, except first it's going to flip a biased coin, and with epsilon probability, just cooperate unconditionally. Otherwise, simulate the other player and copy them. So now if this plays with itself a bunch, like it'll usually simulate, eventually one will cooperate and the other will then cooperate. Yeah?
Is there a microphone?
I just wanted to make the perhaps stating the obvious that one should be very careful about drawing normative conclusions from such experiments because they're very sensitive to the whatever hyperparameter configurations you set. So is it one-off? Is it iterated? If it's iterated, is it a known number of iterations? Are you using a discount factor per iteration? I think there's theoretical work that shows that for a given composition, for a given subset of discount factors and relative payoffs in a generic person's dilemma, there are actually configurations where cooperation turns out to be the measure.
Yeah.
So my point is being, like, how you specify the problem is super important in terms of the tables.
Yeah. Yeah, good point. Yeah, maybe I should have been clear about this. So I'm assuming this is a one-shot prisoner's dilemma, no iteration. The only thing that's different is that we submit programs. But as you're, like, maybe this explanation made you think this way because, like, we're kind of imitating what happens in an iterated game by this thing where, like, we're simulating each other back and forth, and that's kind of like repeating the game. Okay, so this is another cool approach to this problem. It's also extended in very recent work, so this area is still hot if you like that. You can go read this paper. It extends the approach to games with more than 2 players. The issue being that with just one opponent, if we both simulate each other at most once, and there's some probability we terminate, this will eventually end. Naively, if you have multiple opponents, you want to simulate them both, we're going to have an exponential explosion of like simulations and never conclude. But yeah, they get around this with some clever correlated randomness stuff. Okay. Okay, so we've been talking about whether you can get cooperate in equilibrium, but it's not the only equilibrium. Oh, yeah, question.
Just like I guess before I actually ask the question, I would ask: is this like just sort of like So like, preparing the ground for like a more a more realistic version of multi-agent cooperation, or are we going to continue with this thrust for the rest of the talk?
More the latter.
Okay.
Or former, sorry, former.
Oh, the former. Okay. In which case, yeah, that's fine. I was just going to say that like, I think in most practical situations, like agent behavior is based on the belief of the payout matrix, which is not usually given to each agent, right? Like, in most realistic situations, you don't actually know the rewards. Even in money situations, there are often like intangible rewards or discounted rewards and so on. Like, I think that way overshadows any like perfect simulation of the other person you can like pull off in like any realistic AI agent scenario.
Yeah, fair point. I think. Yeah, so there's two types of things. There's like uncertainty over the payoffs. There's also like lack of specificity in the payoffs. So like, I just like pressing the cooperate button and like it doesn't give me higher numerical payoffs, but like I care about other things. Yeah, I think for various reasons, like, I think this is an issue, and like these results definitely I wouldn't expect to like just generalize. But I do think that like strategic agents that are like at this level that are kind of like handling very high stakes situation will mostly act like they have utility functions. Like they'll kind of be, I don't know, maybe they're risk averse or maybe they're not, but they're doing some kind of aggregating over their uncertainty and they're like going on their best guess of the payoffs, and they're like, you can account for these soft factors in utility functions. Maybe we can argue about that later. Okay, so yeah, maybe I should have sped through everything so far, but the point of this program equilibrium stuff is that even though the setup seems pretty good, we get cooperation in Nash equilibrium, we also get other weird asymmetric equilibria. So for instance, if player 1 submits the program, expect this player 2 program below. If so, I'll cooperate with probability only 1/3 and 2/3 defect. Otherwise, I will defect unconditionally. And player 2 submits the program, expect the program above. If so, cooperate, otherwise defect. This is a Nash equilibrium, even though player 1 is only getting like one utility in expectation, which is the same as they could get by just defecting blindly and not doing anything. And player 2 is like getting some really nice outcome where they like get 3 2/3, like 2/3 of the time they defect, the other player cooperates. Yeah, so you can get the, okay, question.
I think you might have switched the player 1 and player 2 in there. Like player 1 is the one that's getting the more utility, I think. That's the one who cooperates only a little bit.
Oh yeah, you're right, yes, sorry, good point, thank you. Right, player 1 is the one who's, just repeating, cooperating with probability 1/3, and so they're the one getting 3 2/3 payoff. Okay, any questions about this? Is this like surprising to people? Is this like is this obvious to people that this was an equilibrium? Thumbs up for obvious. Okay, thumbs down for surprising. Okay, sorry. Yeah, I'm not very calibrated on how much game theory people know. Okay, this result is called the Folk theorem, or it's a Folk theorem. And what it says, so the general characterization of like what payoffs can happen in Nash equilibrium of program games is that a payoff profile can be achieved in Nash equilibrium if and only if it's both feasible and each player gets at least their security level. So feasible just means like you can actually do this. You can't just like give both players 10 utility or something. And security level is what you can get for yourself unilaterally, which is also the same as what the other player can force you to get at most. And so as long as these two conditions are met, you can have a Nash equilibrium getting this payoff. Yeah, so the one we saw before was an example of that, 3 2/3 and 1. You can also have like even worse ones where like both people get like close to 1 or something. I will, I think, skip the proof of the Folk theorem because it seemed like people already knew it. But yeah, the intuition is basically like we can like have programs that expect this to play this strategy, and then if the other person doesn't submit such a program, force them to get their security level. and they will instead, yeah, this will be a Nash equilibrium. Okay, so yeah, the reason why I started with this was to get, with program equilibria, was to hopefully give people an intuition of why the Folk theorem happens. Because the Folk theorem is an extremely common result. So it comes up in program equilibrium. It also comes up if we just repeat the game with high enough probability, as was discussed before. You have to be a bit careful with discounting. It also comes up in one of Vojta's papers where you assume two players are going to play the game, and before they play it, they're going to like simulate themselves playing the game. That simulation will make more simulations, but there's some probability at each step that it fails. This also results in a Folk theorem. And you can also get it in like things that don't even feel like AI recursive stuff, right? So you can get it in this setup where before playing the game, players are gonna take turns playing a disarmament step. And on a disarmament step, basically you can put a maximum probability on any action. So you can say, okay, I'm only gonna defect with probability at most 0.9. And then maybe the other player says, oh, I'm only gonna cooperate with probability at most 0.8. And then you lower your defect probability to 0.8 or whatever. And it turns out that this process also results in a Folk theorem. Any questions on this? Cool. Okay, yeah, it also happens in similarity-based cooperation, where it's like program equilibrium, but rather than observing the opponent's full source code, we just see one real value representing how similar we are. And okay, why am I talking about this? It's an extremely common result, and I think people usually view it as a basically positive result. It definitely enables some good stuff, but it also causes bad dynamics. So one such thing is commitment races. This is supposed to be a picture of like two cars going at each other, but like I couldn't get Gemini to do that for some reason, and no matter how hard I tried. So they're next to each other, but imagine they're like going at each other and they're maybe gonna crash. So that is the like classic story of the chicken game, right? And the idea is that you want to be the first to commit. So for instance, if you are the first one to throw out your steering wheel, then the other player knows you can't swerve, you must dare, and so they're gonna swerve, right? But maybe you then have the other player like wearing a blindfold so they can't see that the other player is throwing out their steering wheel. And you can get like weird stuff like this, right, where people are racing to like commit to decisions before the other player. They're like trying to ignore information from the other player. Maybe they're like committing to stuff without like thinking things through carefully because they want to be the first to commit to this exploitative equilibrium, because then the other player will be incentivized to follow. So this is one bad thing that can happen. And of course, if both players like miscoordinate over who is like going first, or they like somehow disagree over who's going first, like they're both going to crash into each other and it's going to be catastrophic, which is analogous to like submitting incompatible programs in the program game, right? Or in the Folk theorem in general. Another thing that can happen is that, okay, we have this prisoner's dilemma, and now player 2 is an additional action, which I've called bad. It's a really dumb action. All it does is like gives player 2 themselves -5 utility, and the other player -1. So it's like we have prisoner's dilemma, and then player 2 can also like shoot themselves in the foot and like kick player 1 or something. Why would you want this? It seems really dumb, but in the Folk theorem, like this, in Folk theorem settings, this actually enables equilibria that are better for player 2 than without having this action. Because now player 2 can make player 1's security level player 1's security level is -1, right? Because if player 2 does this like bad action, player 1 gets -1. And so now, for example, defect cooperate is a Nash equilibrium. Because player 2 can submit the program. Unless you defect unconditionally, I'm going to play bad. Otherwise, cooperate unconditionally, I'm going to play bad. Otherwise, I'll defect. And player one's best response to this is to just cooperate and let themselves get exploited. Yeah, any questions on this? So to me, the upshots are just that we should be very careful about this kind of any setting that results in a folk theorem, which is very many of them. If you have kind of too much transparency, too much commitment power, you can enable these non-credible threats and you get these bad asymmetric equilibria. You also incentivize people to like be able to add these bad actions to the game, and things get risky. There's ways to try to get around this. We can try to argue about what the best bargaining policy is to get a fair equilibrium, but there's disagreement about these, and like in some sense, equilibrium selection may just be impossible in general, and so yeah, I don't find a lot of comfort in this. I mean, I don't think like these crazy equilibria are that likely, but they're also quite bad. Okay, so now I'd like to talk about another approach, which tries to avoid this folk theorem dynamics. Instead, we're going to look at safe Pareto improvements, which are interventions which guarantee an improvement on the original game, regardless of how the original game is played or would be played. So let's look at an example. Let's again suppose our AIs are going to play a game of chicken, which again is supposed to be analogous also to the playing your program in the program equilibrium setup. So we'll let our AIs play this game however we want, or however they want to, however they like will on their own. Of course, this game has like multiple equilibria. Maybe we don't know what's going to happen. We can't agree to play any particular equilibrium because like we're in direct conflict over that, right? But we'll let our AIs play this game themselves, and then secretly from them, we'll agree that if they crash into each other, in whatever like mechanism that we have, turning the program game outcome into the real world outcome, we'll just replace dare dare with swerve swerve. So yeah, we basically prevent the possibility of this crash outcome. And this, yeah, otherwise if the crash outcome wouldn't have happened, like nothing changes in the game. Yeah, this is a safe Pareto improvement. Any questions? Okay, I was maybe thinking someone would quibble with whether this will really work. Vojta wrote a nice blog post outlining reasons why this won't work. And basically the reason is that like, okay, sure, this is a safe Pareto improvement if the AIs play the new game exactly as they would have played the old game. But of course, we're going to be incentivized to not have them do that, because now dare is a strictly dominant strategy in this game, and we're both going to be incentivized to secretly tell our AIs, don't play the original game, just dare. And if this happens, like the scheme doesn't work at all, right? And it just collapses to agreeing to swerve swerve, which is not, for either of us, guaranteed to be better than the original game. In some recent work, there's also this approach of like designing this new game so that nobody has such an incentive, and then we get a safe Pareto improvement even if people are kind of strategically telling their AIs about the new game. So for this, I need the concept of game isomorphisms. Basically, these are just ways of changing the game, the player's payoffs, that don't change the strategic dynamic. So for instance, if like we just add 1 to player 1's utilities, like this is great for them, but it doesn't change how they should play the game. Their best responses are the same, the Nash equilibria are the same, everything is the same. Likewise, having their utilities, this doesn't change their strategic incentives. And in general, like multiplying a player's payoffs by any positive constant and adding any constant does not change their incentives. It's called an isomorphism. And so the idea is that, okay, maybe we can design the new game to be isomorphic to the original game, but still Pareto better. So now we have this SPI and no one has the incentive to like secretly tell their AIs what's going on. This doesn't exist in that original game that I was showing you, but it does exist in this slightly more complicated game. So what's going on here is that the bottom right quadrant is a game of chicken. It's also, the top left quadrant is also a different game of chicken, which is like much riskier and like slightly better for you if you kind of win, right? So if you get dare swerve, you get 8 instead of 5, but everything else is kind of worse or the same for you. And also the bottom right quadrant is strictly dominant. So by default, we'll expect that the bottom right quadrant just happens. But now in this game, we can create this type of safe Pareto improvement that I'm talking about. And the idea is that we're going to design a new game. We're going to have our AIs play this new game. And then we'll map the outcomes of the new game, which I call the token game, to real world outcomes, which are distributions over the original game. So for instance, like if they play token swerve and token dare, we'll have, in the real world, this is played by 2/3 probability of the risky dare and 1/3 probability, 2/3 probability risky dare, risky swerve, 1/3 probability risky swerve, risky dare. That gives us payoffs of 2, 5. And we're gonna likewise fill out the rest of these by distributions over the original game. And so I hope you'll believe that you can get payoffs like this. And now the upshot is that we're playing this token game instead of the original game. The strategic incentives are exactly the same, but the game is, the isomorphic outcomes of the two games are better for us now than they were before. In particular, we're multiplying our payoffs by 0.6 and adding 2. You can just kind of compare the corresponding entries of the matrix and see that this is better for us. Any questions about this?
I have a question. So, how do you define success? Because I can just how do you define success? Because I can just add 1 million to all of the payoffs, and then it's Pareto improvement over the original game, but that feels like cheating. So what's the difference? How is this, in which way is this better?
Okay, yeah, thank you for that question. Yeah, that doesn't work because you can't actually realize those million payoffs in the real game. But the point here is that this new game we've constructed is not some game with arbitrary payoffs. It's a game with payoffs that are realized by playing strategy profiles in the original game. So, yeah, does that answer the question? Yeah. Okay, cool. Okay, so this SPI stuff is another kind of different complementary approach to interventions that improve games. There's lots more work on this, lots more stuff. I just briefly covered a small part of these 2 papers. And there's lots more work on this, so including, lots of open questions, so if people want to work on this, talk to me or follow these links. Now I'd like to just talk briefly at a more high level about some other things. So, okay, so suppose you're going to play Prisoner's Dilemma, but your opponent is your exact clone. Who's seen this example before? Okay, not that many people. So you're playing a Prisoner's Dilemma, your opponent is your exact clone, you don't care about their payoffs. What should you do? Thumbs up for cooperate, thumbs down for defend. Okay, most people agree, most people seem to think they want to cooperate, which is also what I think. Nobody, for some reason, wants to argue this is unrealistic. Maybe because everybody knows, okay, it may be unrealistic for humans, but it's super realistic for AIs, right? And so with AIs, we get a whole spectrum of potential interactions, not just with copies of oneself, but the whole gradient, right? You can have the same model but a different prompt, or the same same base model but differently fine-tuned, an earlier generation model, different labs model that has like different architecture but same training data, whatever, right? And this strategic interactions in the setting, I think, are very understudied. Yeah.
How would the clone model now is a clone?
Yeah, good question. Yeah, in the original thought experiments just told to you. In the AI case, there's various ways this could happen. I think mainly because if models have an incentive, if models are able to cooperate with similar models to themselves, they benefit from learning about their identities, right? And so there is incentive for them to like set up, well, we could set up infrastructure to allow models to like verify their identities, or they even could have incentive to like make themselves transparent, make proofs about like what source code is being used to output the action, sorry. And yeah, and so this could, basically cooperation is possible, and so, and there's ways of verifying identities, so there's kind of incentive to do so.
If there's a will, there's a way.
Can I?
Yeah.
Yeah, probably this was one of the answers was in Louis' talk about AI ID, agent ID, because probably we have no choice in implementing something like that, and that's one of the solutions, because 100% there will be a base model in this ID. And one thing which you mentioned some examples why they may differ, even having base models, and I think one of the reasons is long-term memory, because I cannot imagine AI agents, personal AI agents without long-term memory.
You don't think they'll have long-term memory?
I think they will.
They will, okay.
Because at least personal database, this is what they will have.
Yeah. Yeah, so I think there's like one interesting thing you're bringing up here, right, is that like if we have longer term memory, like whatever is context or memory is getting longer, now the models are drifting apart, getting more different, maybe they're no longer like willing or able to cooperate with other versions of themselves that are the same base model but like different memory. Yeah, so like I said, I think there's lots of interesting things here. Not much work on it. Someone should do it. Yeah, one model for this is similarity-based cooperation, which I talked about briefly before, where you have models and they get a signal about their similarity. This is one way of like formally modeling what should go on here, but I think we need to think about how to do this practically and what will happen practically. Okay, another thing which maybe Vojta will talk about more, so I won't go too much into this, but yeah, using game theory tools for AI evals and AI control. Just some work to be aware of here: simulation games, study games where one player can pay a small cost to learn the other player's strategy. This is mostly framed right now in the literature in terms of one human designing an AI, another human interacting with it, and the two of them kind of using the fact that one player is delegating to an AI to achieve more cooperative outcomes, Nash equilibria that are better than any Nash equilibria in the original game. But I think this has obvious relevance to AI evals. And yeah, there's lots of open directions here, so yeah, people should talk to Vojta about this, or me, or Louis. We have one paper on this in the works, but yeah, I think Vojta knows the most. Yeah, another kind of area of research relevant to control here is that on games with imperfect recall. So of course, AI models can have multiple instances that are running in parallel or just serial, but they don't have persistent memory. And so they won't know what actions other instances have taken. we can model this with games with imperfect recall, but it's very understudied in the game theory literature because this can't happen with humans. And so, yeah, there's some recent papers on them, which are nice papers, but they're like just kind of laying the very foundations, like even figuring out how to define Nash equilibrium here, and establishing like the very basics of the complexity theory results. So I think it'd be great for people to look at trying to apply this to AI control, which, yeah, as I mentioned before, and I think someone also mentioned earlier, is this setting where we're trying to get work out of potentially misaligned AIs. Okay, and one more paper here, imperfect recall in AI delegation. It's in this setting where we have human overseers. They have a black box AI. The only thing they can do is they can test it up to n times, and then they have to decide whether to deploy it or not. The AI can't distinguish the tests and deployment, so it has to play the same strategy in both. It also has imperfect recall, so it can't remember what it did in previous tests. And it only has two actions. It has a good action and a bad action. Well, one action which is good for the overseers, and also good for the AI if it's aligned. And it also has an action that's only good for the misaligned AI and bad for the overseers. So it's a very simple model, but they get some nice, interesting results out of this. Yeah, also I should mention that this setting kind of only makes sense if the overseers can tell whether the action was good or bad after it's been taken, but they don't know ahead of time in a given game which action is good, because then they could just do it themselves. So like I said, it's a nice paper, people should read it. I think it's also obviously very simple model, and so you could do lots of extensions and get lots of interesting results. Okay, finally, one more kind of topic, AI for improving negotiation. So this is more in the domain of using AI tools to help humans cooperate. Here's one idea. So let's say I want to sell you some information. It's for example, an idea to improve your business. It's something, so I tell you I have this great idea for your business. You should pay me $1 million and I'll tell you it, because it's going to make you $2 million, right? Well, you're never going to buy this without hearing the idea. But also, if I tell you the idea, you're never going to pay me afterwards. I can try setting some mechanisms up, or you can sign an NDA, but it's tricky, it's brittle. Humans can't forget things. They can't just act as if they didn't hear the idea perfectly. And so one idea here is, okay, well, I will tell an idea to your AI. Your AI evaluates whether you want to buy the idea. If it does, it sends that up to us, and we can prove that the idea I tell you is really the idea I told the AI, and you can pay me for it. Otherwise, the AI just forgets, and we don't have this problem of me revealing the information. So I think, these are kind of nice examples to have in mind that people have had around in theory, but maybe AI is getting close to the point where this becomes practical, and thinking about it is good. Yeah? No.
No, that's probably
Okay. Okay, and I just also wanted to note that this idea isn't completely new, so we can already do similar things with cryptography. So if we're in some kind of scenario where I want to sell you something, now it's just a normal good, so we know what it is, but how much we each value the item is secret. And so we want to check whether your willingness to pay is higher than my willingness to sell the good. We want to actually make the trade if your price is higher than my price, and let's say we just meet in the middle. But otherwise, our values should stay secret. Of course, we can't, just naively, we can just tell each other the values. That doesn't work. But there is cryptography that will let you do this, that will, let you compare these two numbers, only reveal if a sale can be made. And so, kind of a proof of concept that this type of idea is realistic, and that AI might let us extend it to non-mathematical settings, where, yeah, instead of just comparing two numbers, you have to evaluate the worth of an idea, which you can't do mathematically. Okay, yeah, and one more thing in this negotiation framework. So I think it's pretty well known that private information is a major obstacle to avoiding conflict. Here's two citations for that. So say we're negotiating about a potential war or how to reach a peaceful settlement. We each have private information about our chances of winning the war, right? We know, or we have like spies. Maybe I know about some of your spies, or maybe I have some of your spies are double agents. We have secret information about our military capabilities. All of this stuff, like, we don't want to just reveal because it loses some of our strategic advantage. And it also is stuff that we're going to be incentivized to lie about, to frame ourselves in a better bargaining position than we in fact are. So, yeah, often, like, you can't credibly disclose any private information and we get conflict. But yeah, here's another case where maybe AI can come to the rescue. We'll have our AIs go into a secure box and negotiate on our behalf. Now the AIs can like reveal the private information to each other. Maybe to some extent they can also verify each other's private information. And we should think about how to make that work. And then only agreement can come out of the box, but none of the private information. So there is like one paper that basically looks at this idea. It studies this in kind of the most favorable possible assumptions where all information is verifiable and the players are committed to following what the box recommends. But yeah, I think both looking at how to do this practically and also in slightly less favorable assumptions, like where the players may not be committed to following what comes out of the box, but instead has to be worth following for the players, is good directions for work. Okay, I think that is my last thing, basically. So yeah, just to briefly summarize, mostly talking about the foundations of cooperative AI, game theory for AI agents, how to formally study strategic interactions involving AI systems, and how to leverage features of those interactions to achieve cooperation. For motivations varying between like powerful interactions between powerful autonomous AIs, AIs that are aligned to humans and acting on their behalf under their supervision, or studying AI control and AI evals. And yeah, hopefully I've convinced you that there's lots of open directions to research. So like Lewis said, get involved, talk to me, talk to him, talk to Vojta. And yeah, if you want to learn more, you can look at the Cooperative AI Foundation website, or you can look at the Focal Lab at CMU. Okay, thank you.